This video will conclude chapter 18. I will go over chapter 18.5 to chapter 18.9 and skip chapter 18.8. In chapter 18.5, we're going to look at how to compare the strengths of the acids. In the previous lecture, we looked at the K values to compare the strengths of the acids, right? So the higher the K value, the stronger the acid is. But what if we don't know the K value for this acid? How can we compare their strengths? And so first, let's look at this acid that are non-metal hydrides. Right, so non-metal hydrides means that the hydrogen is bonded to a non-metal, right? So form this covalent bond. In this example, we're gonna look at the nonmetals in column 7 on the periodic table, right? So those are the halogens, right? So when because they're in the 7th column, right? So they will bond with one hydrogen, right? So that will obey the octet rule. So to compare their strengths, we're gonna look at the electron negativity of these nonmetals. Right, so the rule is that the higher the electron negativity, the weaker the acid. And why? If you consider the bond between the hydrogen and the nonmetal. Right, so the bond between the hydrogen and the nonmetal. So for this molecule to act like an acid, right, its ability to donate the proton. Right, if this bond is very strong, right, that means if the nonmetal has a very high electron negativity, which will make this bond very strong, it's gonna be very difficult, right, to remove that proton, or it's gonna be very difficult for the acid to donate that proton. So that will make it a weak acid, right? In this example, fluorine is the one that has the highest electron negativity, right? So its bond energy is gonna be the highest, right? So it's the weakest acid, right? So it has the weakest acid strength. But for iodine, because it has the lowest electron negativity, so the bond is weaker, so it's more easier for the molecule to donate that proton. So it's gonna generate a lot of protons, so that will make it a strong acid. Right, so for the nonmetal hydrides, we can just look at the electron negativity of the nonmetals, right, to compare their acid strengths. So the higher the electron negativity, the weaker the acid. Next, we'll look at the oxo acids, right? So for this type of acid, the hydrogens are not bonded to the nonmetal, but actually bonded to an oxygen, which is bonded to the nonmetal, right? So this type of acid could have one or more than one oxygen atoms, right? So to compare their strengths, we're gonna not only look at the electron negativity of the nonmetal, right, but also look at the number of the oxygen atoms, right, around the nonmetal. Right, so we have two scenarios in this case. So the first scenario, we have the same number of oxygen atoms. Right, so we have same number of oxygen atoms. So the rule is that the higher the electron negativity of the nonmetal, the stronger the acid is. Right, so let's look at these three acids. Right, so the L have one oxygen. Right, so based on the rule, we will compare the electron negativity of the nonmetal. Right, so chlorine is the one that has the highest electron negativity among the three, so that the corresponding acid will be the strongest. Right, so I hope you guys still remember how to name this type of acid. Right, so this is called the hydrochlorous acid, hypochlorous acid. Right, start with the hypo because only have one oxygen. So this is hypobromous acid, and this is hypoaldous acid, right, with the OUS at the end. So again, because chlorine is the one that is the most electronegative, right? So this hypochlorous acid is the strongest, right? or if you look at their K values, right? So this acid has the highest K value among the three. And if you look at the structure of this acid, which is here, right? So basically, the hydrogen is bonded to the oxygen, right? So basically, we're comparing the strength of this OH bond, right? So if this nonmetal has a very high electron negativity, right? So that will pull more electrons away from the oxygen, right? So there is less electrons available to form the OH bond, so that will make this OH bond weaker. So it's easier to donate the proton, right? So that will increase the strength of the acid. Right. So for the second scenario, we have the same nonmetal but different number of oxygen atoms around that nonmetal. Right. So in this example, we have the same nonmetal, which is chlorine, right? But we have a different number of oxygens, right? So increase from 1 all the way to 4. And again, to name this acid, right? So this is called hypochlorous acid, right? So this is called chlorous acid, right? Without the hypo. This is chloric acid, and this is perchloric acid. Not hyper, right? Just perchloric acid. If you look at their K values, right? So for hypochlorous acids, it's 10 to the negative 8, right? But for the perchloric acid, it's 10 to the positive 7, right? So difference is huge. And why? Again, let's look at their structure, right? So again, we compare this strength of this OH bond, right? Because to be a strong acid, this bond must be weak, so the proton can be easily donated. So if you have more oxygen around this nonmetal, right, that will means that there's gonna be more polar, right? So more electrons gonna be pulled away from the hydrogen, from the oxygen that is bonded to the hydrogen, right? So that more oxygen meaning that will make this OH bond weaker, so the hydrogen is easier to be donated. So the strength of the acid will be stronger. Right, so let's conclude. Right, for oxalic acid, if you have the same number of oxygen, just compare the electron negativity. Right, so the higher the electron negativity, the stronger the acid. Right, if you have the same nonmetal but different number of oxygen atoms, so the higher the number of oxygen atoms, the stronger the acid. In chapter 18.6, we're gonna look at the weak bases and their relationship to weak acids. The content in this chapter 18.6 is very similar to the content for the weak acids, and the type of calculation problem is also very similar. For acids, we have this dissociation constant Ka, right? So for base, we also have this constant called base dissociation constant Kb, right? But actually, the base never dissociate, right? For acid, right, it will kind of like decompose, right? So the acid molecule become proton and the corresponding anion or the conjugated base, right? For the base, for the weak base, it actually doesn't dissociate, right? So only the strong base, right, they will dissociate. But for the weak base, it is generating the hydroxide by getting a proton from the water, right? But we still call it a dissociation constant anyway, right? So for example, if you have a weak base in this case, right, so you get a proton, right? You get a proton from the water, right? So generating this conjugated acid and the hydroxide, right? So for the equilibrium constant Kc, right, we can express it like this, and again, for the same deal, because water is the liquid, right? So we can delete it, right? So for the Kb, right, the expression is gonna be the conjugated acid times the hydroxide divided by the base. right? So this is the same concept as Ka, right? So for the pKb, which is the native log, remember if you put a p in front of a constant, that p is a native log, right? So that's an operation of native log, right? So the native log is p, and so the kb value will be equal to 10 to the negative pkb value. Right? Exactly same for the Ka. Right? So it means the format is exactly the same. Right? So to compare the strength of the base, right? The stronger the base, the higher the kb value. Right? So because pkb is the native log, right? So that means the stronger the base, the lower the pkb value. So don't confuse between this kb and the pkb. Right, so in this table, you see the Kb value, right, for this different type of weak bases, right? So we know that ammonia, right? So ammonia H3 is a weak base, and that's the example we use in the previous lectures a lot, right? So for the amines, right? Amines are the molecules that contain this hydrogen bonded to the nitrogen, right? But also the nitrogen is bonded to some carbon chains, right? So those molecules are called amines, right? So again, the amine, right, act like a base, right? The same way the ammonia does, right? So the lone pair on the nitrogen, right, it will attract a proton from water, right, which is this indicated by this arrow, right? And then the hydroxide is generated, and you generate the conjugated acid. So similarly, right, we can also calculate the pH from the Kb value. And we have an example. So here we have this dimethylamine, right? So have this formula, and the Kb value is given. So it asks us what's the pH of this compound in the solution if the concentration is 1.5 molar, right? So the approach to solve this type of problem is the same of solving the K or the pH from the weak acids, right? So first you write down the equation, right? So for this base, you have the base and the react with water, right? So generating hydroxide and the conjugated acid. Right? Remember the conjugated acid will have a one more positive charge, right, than the base. So to express Kb, we have the conjugated acid times hydroxide divided by the base. So now let's list this ICE table. Right, so we know the initial concentration of this base, dimethylamine, is 1.5. Right, so for the product, the concentration is 0. So because the coefficients are equal to 1, right, so we can say the amount of this product produced is equal to the amount consumed. Right? They have, so for the equilibrium concentration for the base, the concentration becomes 1.5 minus x, and for the product we have a positive x. Right? So don't forget that we can also make assumptions. Right? So because the Kb value is very small, right? It's 10 to the negative 4th. So we can assume that this x is gonna be very small, right? Because the small Kb value means the equilibrium position is far to the left, so there's very little amount of product generated. So we can ignore the consumption, right, from the original concentration. So we'll say the 1.5 minus x, right, which is the initial minus the amount lattice, is almost equal to the initial concentration, which is the equilibrium concentration, which is also almost equal to the equilibrium concentration. Right, so when you calculate Kb, instead of have 1.5 minus x, right, we just use 1.5 to simplify our mass. Right, so let's get rid of this minus x. Right, so if you calculate x using this equation, we're gonna get 3.0 times 10 to the negative 2 molar. And remember, you have to compare this, right? Compare this number with 1.5. If you divide this number by 1.5, you're gonna get a percentage lower than 5%, right? So that means our assumption is valid, right? So we'll stick with this value. So that means the hydroxide and the conjugated acid, the concentration at equilibrium, their concentration is gonna be 3 times 10 to the negative 2. Right, so based on the Kw, which is 10 to the negative 14, we can calculate the proton concentration based on the hydroxide concentration. Right, so the proton concentration is going to be 10 to the negative 14 divided by the hydroxide concentration. Right, so this will be the proton concentration, and then you can convert that into pH. Right, so it's exactly similar approach, right, as the way we solve the equilibrium problems for weak acids. So earlier when we look at the dissociation of weak acid, right, we said for weak acid the anion is the conjugated base, right? So this is a conjugated base, this A minus. Right, so you can actually see, right, the relationship between the weak acid and the weak base. Right, so when this weak acid loses the proton, it becomes a base. Right, so for this weak base, right, so when it dissociates, or we shouldn't say dissociate, but so when it reacts with water, right, by taking that proton, it will generate this hydroxide. Right, so that's why we call it a base, right, because its ability to generate hydroxide. So if we start with a weak acid, right? If we start with a weak acid HA, right? So because it's weak, right? So the amount of this A minus generated is gonna be very small, right? So if this A minus continue to react and generate this base, and this because a weak base, right? So the amount of hydroxide generated is going to be way smaller, right? Even smaller compared to the amount of the proton generated in the first step. So overall, if you start with a weak acid solution, right? So the proton generated is going to be way higher than hydroxide generated, right? So the solution is going to be acidic. Right, so but if you start with a metal anion solution, for example, a sodium, say a fluoride, right? So fluoride is a weak conjugated base of the hydrofluoric acid, right? So if you start with this A minus solution, you cannot introduce the anion by itself, right? So it must come with a metal, right? So when this salt dissolves in water, it's gonna totally dissociate, right? So the sodium cation is gonna be the spectator ion, which is not involved in this reaction, right? So for this anion, right? So for this anion from this weak acid, if we start with this solution, the solution is gonna be basic, right? Because for this anion, it's gonna generate some hydroxide and also this weak acid. And this weak acid will further react and generate some proton. But the amount of proton generated will be much smaller compared to the amount of hydroxide generated in the first step. And so that solution will be basic. For a conjugated acid and base pair, we can actually relate the K and the Kb value with the water dissociation constant Kw. Let's see how can derive that relationship. So first, you have a reaction which is the weak acid, right, donated proton, and you also have a weak base, right? So the base is the conjugated base of that weak acid, right? So you have this second reaction. So for the first reaction here, when you express the K value, right, you can write it like this, Right? So this circle here, so that is the Ka expression, right, for the first equation. And for the second equation, for the base to generate the hydroxide, the Kb value can be expressed, right, using these terms. Right, so this is the Kb value. And if you multiply them, right, some terms cancel out, and you ended up with the proton and the hydroxide. We know that when you multiply these two, they're equal to Kw, right, which is the water dissociation constant. So we can say that for same conjugated acid-base pair, as for the conjugated acid and base, their K value multiplied the Kb value is going to be equal to the Kw. Right, so at room temperature, we know that the Kw is equal to 10 to the negative 14. Right, so if we know one of these K values, we can calculate the other one. For example, for hydrofluoric acid, if we know the K value is 6.8 times 10 to the negative 4, we can calculate the Kb value directly, right? So by doing this division. Right, so for the Kb value, again, this fluoride, right, which is the conjugated base of this acid, right? So it could be a start with a NaF, right, or potassium fluoride. Right, so again, you cannot introduce the anion by itself, right? So normally in the question, you're gonna see this anion or the conjugated base is accompanied, right, by a metal, right? So the whole ionic compound is introduced into the solution, not the anion itself, right? So that means for hydrofluoric acid, right, you can say if you compare the hydrofluoric acid and say sodium fluoride, right? So if you want to know the Kb for this, right, so we only worry about this fluoride, right? So we don't care about what's the metal. It could be sodium, it could be potassium, right, cesium, whatever, right? So these are the so-called conjugated acid and base pair. In chapter 18.7, we're gonna try to determine whether a salt solution is acid or base, or acidic or basic. Right, so again, a salt is a ionic compound, right? So when it dissolve in water, right, become cations and anion, right? So the dissociations almost achieve 100%, right? So that's called salt solution. So when you dissolve a salt, right, into a water, so generating this solution, the solution could be either neutral, acidic, or basic. And so when this salt contains the anion of a strong acid and the cation of a strong base, the resulting solution will be neutral, right, because both ions do not react with water. For example, if we have a sodium nitrate, right, because the anion, which is the nitrate, right, so the nitrate is from the strong acid, right, because nitric acid is a strong acid, right? So this nitrate, it will not react with water, right? So it will be hydrated, will be surrounded by the water molecules, but it will not react with the water molecule as a weak acid or weak base does, right? So that will not change the amount of proton and the hydroxide when you have this anion introduced into the solution. Right, so for sodium, right, sodium is from a strong base, right? So sodium hydroxide or sodium oxide, right? So because it is sodium from a strong base, it also does not react with water, right? When it exists in water, this sodium cation will be surrounded by the water molecules, but it will not react with water molecules. So it doesn't change the amount of proton of the hydroxide. Right, so when you have this sodium nitrate, right, so generating these two ions, and both of them do not react with water, you're gonna generate with a neutral solution. right? So here the table gave you this, not the table, the list, right? Gave you the type of anions and cations, right? That are from strong acid and base, right? So they do not react with water. Right? If you have a combination of any of these cation and anion, that means the salt solution for this compound will be a neutral solution. When you have a salt that contains the cation of a weak base and the anion of a strong acid, and when this salt dissolves in water, the solution generated will be acidic. So let's take a look at example. Suppose we have this compound, right? So ammonium chloride. So when this compound dissolves in water, it will generate a ammonium cation and a chloride anion. Right? We know that this ammonium plus NH4 plus, right? So it is the conjugated acid of ammonia. Right? So when ammonia dissolves in water, right? So when ammonia dissolves in water, it generates this ammonium ion and hydroxide. Right? So we say this NH4 plus is the conjugated acid of ammonia. Right? So it's a very weak acid. Right? So when this ammonium dissolve in water, right? So it will generate ammonia and this proton. So this ammonium will act like an acid. So it is the cation of a weak base. Right? So, but if for chloride, right? Again, chloride it is from a strong acid, right? So hydrochloric acid. So it's the anion of a strong acid. So chloride, it doesn't react with water, so it has no effect on the pH or the amount of proton or hydroxide in water. So because ammonium will generate proton, right? Chloride does nothing. So the overall effect will be that the solution is going to become acidic, right? Slightly acidic. When we have a salt that contains the anion of a weak acid and the cation of a strong base, and when that salt is dissolved in water, the solution will become basic. Right, so the example will be this sodium acetate. Right, so it's actually a sodium cation. Right, so the sodium is actually bonded to one of the oxygen. Right, so the acetate remember has this carbon oxygen double bond and a carbon oxygen single bond, and then bonded to this methyl group. Right, so this is a sodium acetate, and when it dissolves in water, right, so this bond will be broken, so generating this sodium cation and the acetate anion, right? Because this acetate is the anion of the acetic acid, right? So acetic acid is a weak acid, right? So this acetate is the anion of a weak acid. Right? But for this sodium cation, right, is the metal cation from the strong base, right? So a couple slides earlier we said that, right, for the metals cation in the first column and most of the metal cation in the second column, right, they are the cation of a strong base, right? So they don't react with water, right? So in this case, because sodium doesn't react with water, so it has no effect on the pH, right? For the acetate ion, because it is the anion of a weak base, right? So it's the conjugated base of acetic acid, right? So when it dissolves in water, it acts like a base, so it will generate hydroxide. So the overall effect will be the solutions become more basic, right? Because the production of this OH. So if a salt contains a cation that is a weak acid, right? So if it contains this cation that is a weak acid, and it also contains an anion that is a weak base, we have to compare the K and the Kb values to determine whether the solution is acidic or basic. In this example, we have this compound ammonium cyanide. So when it dissolves in water, it will become a NH4 plus, so that's ammonium, and the cyanide is Cn minus. Right, so ammonium we talked about earlier, right? So it is the conjugated acid of ammonia, so it is a weak acid, right? So this cation, positively charged cation, right? It is a weak acid. So when it reacts with water, it will generate a proton. And for cyanide, it is an anion and it is a weak base, right? Because it's the conjugated acid, it's the conjugated base of cyanic acid. So when this cyanide reacts with water, it will generate hydroxide. Right, so you have ammonium generating proton and cyanide generating hydroxide. Right, so to determine whether the solution is acidic or basic, we have to compare, right, the amount of the hydroxide and the proton. Right, so whichever is higher, that means that will determine whether the solution is acidic or basic. Right, so and the amount will depend on the K and the Kb value. Right, so in this case, because the Kb value for cyanide, right, is higher than the K value for the ammonium, right? So the values are given here. So because Kb, right, Kb is greater than Ka, that means you have more hydroxide, right, generated than the proton generated. So overall, you have more hydroxide, right? So that will make the solution basic. So if you have another salt that has it contains this weak acid and base, and the Ka value is greater than Kb, the solution will be acidic. Chapter 18.8 is skipped, so it won't be on the exam. Right, so for chapter 18.9, I'm also gonna just introduce this concept, and I won't include any of this content in the exam. Right, so but I want you to know that this type of acid base, right, because it's very commonly used in organic chemistry. Right, so 18.9 introduced is called Lewis acid and base. So far we have talked about two definitions regarding acid and base. Right, so first we have this Arrhenius acid and base. Right, so then we have this Bronsted-Lowry acid and base. Right, so for Bronsted-Lowry acid and base, we highlight this proton. Right, for the acid, it donates a proton. For the base, it accepts a proton. And the last definition about acid and base is called the Lewis acid and base. Right, so for a compound to be a Lewis acid, by definition, it is an electron pair acceptor. And for a Lewis base, it's the electron pair donor, right? So you highlight this electron pair other than the proton, right? So if you look at this simple reaction, right? So the A is the Lewis acid, right? Because it's the electron pair acceptor. It will accept that lone pair of electron from the base. And for this Lewis base, right, it is based on definition is the electron pair donor, right? So it donates the electron pair to the acid, and the species formed, right? So it's called the adduct, right? So the adduct is the new species formed, right, which have this new formed bond, right? So when this A and B are bonded together, right? So you form this new bond. And this whole the entire species called this adduct. Right. For example, when you have a boron boron trifluoride, right? So for boron trifluoride, it will act like a Lewis acid, right? Remember, boron is the one that has electron deficiency, right? So as a central atom, right? So when it met another molecule has this lone pair of electrons, right? For example, ammonia, right? So this electron deficient boron is desired to get this lone pair from the nitrogen, right? So they will form this boron nitrogen bond, right? So right here. So after they form this bond, both boron and the nitrogen are obeying the octet rule. Right, so in this case, because this boron accepts a lone pair from the nitrogen, so it is the Lewis acid. And because the ammonia, the nitrogen donate that lone pair of electron, it is the Lewis base. Right, so again, this boron accepts the lone pair of electron, so it's the Lewis acid. So Lewis acid is the electron pair acceptor, and the base is the electron. Lewis base is the electron pair donor. Right, the product, right, contain this newly formed bond is called the adduct. And here we have another example of a Lewis acid and Lewis base reaction. Right, so for this Lewis acid sulfur dioxide, because oxygens are more polar than the sulfur, right? So mean more electronegative than sulfur, right? So each of these oxygen sulfur bond are polar, right? So meaning that the sulfur is kind of like electron deficient because the electrons are pulled away by the oxygen, right? So when this molecule met another molecule which has this lone pairs of electrons, right? For example, water, right? We have lone pair electrons on oxygen in water, so they will react, right? So they will react and form this product, right, which contain this newly formed sulfur oxygen bond, right? So this is called a adduct, and because this sulfur dioxide it accepts that lone pair of electrons from oxygen in water, it is the Lewis acid, and the water in this case will be the Lewis base. And you can see for this type of acid and base, right? So it doesn't have to follow the concept that the acid must be contain hydrogen, right? So both of these molecules do not contain hydrogen, but they're still acting like an acid. But in this case, it is a Lewis acid, right? We can say they are the Lewis acid because they are the electron pair acceptor, but they are not the Arrhenius acid or the Bronsted Lowry acid. And in fact, a metal cation is also a Lewis acid, right? Because it has the ability to accept lone pair of electrons. So when you dissolve a salt in water, right, so contain this metal, so this metal will become a cation. That cation doesn't exist in the water by itself. It's actually surrounded by water molecules. We call that a hydrated metal cation, right? So because the metal cation has a positive charge that will attract the electrons, right? So from the water molecule, because you have lone pair electrons on the oxygen, right, in the water molecules. So those electrons, right, give this partial negative charge on this oxygen. They will be attracted by the positively charged metal cation, so form this hydrated metal cation, right? Because in this case, the metal, right, accept the lone pair electron from the water, so this metal cation is the Lewis acid, and the water is the Lewis base. So I have one homework question for chapter 18.5, one for 18.6, and then one for 18.7. Right, so for 18.6 is the problem 18.106. Right, so this is for the chapter 18.6. So the problem asks you what's the pH of 0.26 molar aniline, right? So which is the amino acid, right? So in the textbook, it doesn't give, in the problem, right, it doesn't give you the formula or the equation and the Kb value for this amino acid, right? So I'm giving you them right here. So this is the equation you should use. right? So you can see why aniline acts like a base, right? Because it generates a hydroxide, and the Kb value is equal to this. And using this information, create the ICE table and calculate the pH of this resulting solution. At the end of this video, I'd like to talk about the timeline for this course before the third midterm exam. Because the schools are cancelled this week, so we have to delete some content, right, in chapter 18 and 19 to help us keeping up with our schedule in the syllabus. But that's very difficult, right? So that's why I highly recommend you to watch the videos on chapter 18 before next Monday. Next Monday is March 23rd, right? Because after today, I'm gonna keep posting the videos on chapter 19. So you don't want to save all the videos until next week. That's gonna be too much content for you to digest within 1 week, and because you have the midterm right after, right? So again, I highly recommend you to finish these 3 videos on chapter 18 before next week. So the first video was chapter 18.1, 18.2, right? The second is 18.3, 18.4, and this is the third video on chapter 18. And do the homework, and also if you have questions, right, email me, leave a comment, or you can FaceTime or Skype, right? So I found those are easier than email. And for chapter 19, I probably will post 2 or 3 videos, right, based on the length, because for a 1-hour video, the file size is very big, right? It takes forever to convert. So I might post 3 videos, each with 40 minutes length, right? So the overall length will be 2 hours, right? So that will be done before next Monday, I think, right? So I hope I can have all the videos regarding chapter 19 posted before next Monday and Tuesday, so you can watch them and study the exam in advance, right? If you have any questions, email me, text me, or comment below. And because this week we don't have class, right? So I'm not gonna check the number of views, right? So but next week, right? Next week the online courses officially start, and I will pay attention to the number of views, and also maybe your comments or your questions will be the way that I consider your attendance or your participation grade for this course, right? So please be active, and also do not save everything until the last day, right?